So this topic is data link control protocols, and so we're still on the data link layer. We've before the midterm, and you've answered questions about how to transmit data across a link using signals, the ways to encode data into signals, bandwidth, data rate, all those factors that impact upon our performance. The last topic we looked at what happens if there are errors. We can detect errors, error detection, and in some cases using forward error correction we can correct them. We're going to look at one last part related to the data link. One of them is about errors and the other is about flow control. Let's see if... So first let's talk a little bit about data link control protocols, or simply data link layer protocols. Protocols part of the data link layer, the second to bottom layer. Physical layer from a simple point of view is about sending bits or sending data as signals across some link. But to make that communications across the link work well, we need some more functionality, some more control and management of that link. And that's what we're talking about here with data link control protocols, controlling the communications across that link. So some features that are necessary, not in all protocols, but in some systems, we often transmit our data as a block of bits. And we can refer to that as a frame. A sequence of, say, 100 bits is one frame. And then we transmit another sequence of 100 bits as a second frame. The transmitter and receiver need to be synchronized to know where, so the receiver knows where is the start of the frame. If we start transmitting one frame, and then immediately after we transmit the second frame, the receiver needs to know where do we distinguish between the first and the second frame. So there's some functionality needed in some cases to synchronize the transmitter and receiver. We're not going to touch upon how that works. There are some stuff in the textbook that explains that in a little bit more detail, but we don't have time for that this semester. Two things we'll go through in some detail is flow control and error control. Error control we know about. If there are errors, and in fact there are almost always errors, how do we fix them? How do we detect them and how do we correct them? We've seen forward error correction is one approach. We'll see another approach shortly, or at least in this topic. Another thing is what happens if we've got our transmitter, it's sending data to the receiver, but the receiver is a slow computer. It's a slow device. So what does the receiver do? It receives the data and passes it up to the next layer for it to be processed. So if the receiver is slow in processing the data and passing up to the next layer, then if the sender is sending too fast, it may overflow the receiver. We'll talk more about that today. And therefore we need flow control. Addressing the two endpoints which are communicating often need addresses. What are the format of the addresses? How do they know addresses? That's often part of data link control protocols. The IEEE 48-bit MAC addresses, which every device normally has. If you've got wireless LAN or Ethernet interface on your device, you usually have a fixed MAC address. That assignment of the address and the definition of the address is part of the data link layer. And other features are necessary for managing the link. Make sure the link is up and running before we send data, to set up the link. And in some systems we need to, when we finish sending the data, to turn off the link, tear down the link. We're going to focus on flow control and error control, which are perhaps the two most important features. And also we'll see that these features come out not just in the data link layer, but also in the transport layer and other layers. So they're more general concepts than just the data link layer. So flow control is the first thing we'll go through today. So the problem is that we have a transmitter, this box here, and this is showing from the data link layer's perspective, and a receiver, and connected by a single link. So the physical layer is about taking the bits and sending in some signal. What type of signal, we don't care in this example. You know the different types of signals we could send. And in fact, the data that we want to send comes from the higher layer. And if you remember your 5-layer stack, at the bottom is physical layer, data link layer, then above that is the network layer. And above that we have the transport and application. So a user sitting at a computer presses the send button to send some data, and it flows through the layers, and eventually a packet of data comes from the network layer and is passed to the data link layer. And it's normally put inside some memory. This is all happening inside the sending computer. It's communicating between components inside the computer. So if we have some data, a packet, say of 1,000 bytes, then that is saved in memory allocated for the data link layer protocol. That memory may be on your part of your computer, or it may be memory physically on the network device. There may be a memory chip on your LAN card, for example. So it's put inside some memory or a buffer, or sometimes we think of it as a queue, because it normally you put one packet in and then the next packet comes and joins the end of the queue and so on. And when the transmitter is ready, it processes the first packet in the queue, creates a frame, adds the header and all the things that it needs to do, and transmits that frame as signals across the link. And then it will transmit the next frame if it has data available. And then the frame is received, and at the receiving data link layer protocol, the receive frame is put inside memory at the receiver. And when the receiver is ready, it processes that and sends it up to the network layer. Of course, the memory we have allocated here is limited in size. It's not infinite. So we may have a problem, especially if we consider the processing of the frame and sending to the network layer, the receiver, is much slower, and which the source can transmit. What can happen, we're transmitting frames, we've got many to send, we transmit them, they come in, they're put inside the buffer or the memory here, and this takes a long time to process each frame. So as it's processing the first frame, another 2 frames come in and put inside the buffer. And as it processes the next frame, there's more frames arriving. They're all stored inside this memory here. And because we have a finite amount of memory, it may fill up. What happens when the next frame arrives, but the memory is full? Overflow. What is the result of an overflow? Error. We lose data. That is, let's say this memory can hold 5 frames at a time, a maximum size of 5 frames. It currently stores 5 frames. If we transmit the 6th frame or another frame, it arrives. What can the receiver do? It cannot save it in memory because there's no more memory allocated. So it can either discard that frame that is received, so we lose data, or it could discard one of the frames already in memory and accept the one that was received. But again, we lose data. So the result of this overflow of memory is that we lose data. And if we lose data, well, this is errors, and we need to do something about it. We don't want to lose data. We'd need to fix that if that happens. So this overflow of the memory is a problem that we want to avoid, and we use flow control to try to avoid that problem. So flow control aims to ensure that the sender does not overflow the receiver. That is, control the speed at which the sender sends such that the receiver is not overflowed. In our previous case, if we could accept 5 frames in the buffer and the buffer is currently full, somehow we need to tell the sender, do not send any more. And that should avoid the error. And that's what flow control protocols do. They control the speed at which the sender sends such that we don't overflow the receiver or the buffer at the receiver. So if the sender sends too fast for the receiver, we get an overflow of the buffer at the receiver. The result is that we lose data. That's a bad thing because we may need to retransmit, or we may need some other way to recover from those errors, and that reduces performance because we waste time retransmitting when we'd prefer to spend it transmitting the real data. So flow control tries to prevent this buffer overflow at the receiver. And we're going to look at two typical examples of flow control protocols. Very basic schemes, but work. And when we look at them, we're going to assume that there are no errors in the link transmission. That is, if I transmit a frame, the receiver will receive that as is. It will not be lost across the link. There will be no errors at the receiver, just in the cases that we look at. In the design of the flow control protocols, we'll assume there are no errors across the link. But there may be different delays across the link, different processing delays at the devices, different transmission and propagation delays. Flow control is important because it's not just part of the data link layer, it's also a key part of the transport layer in TCP. When you download a file with your web browser or any application, most likely you're using TCP, and that is implementing a flow control algorithm. And understanding how it works helps you understand the performance of your download, what limits the performance of your download. So we're going to look at two flow control protocols, just one today, the first one. Before that, we're going to try and explain a way to illustrate protocols. So this is not specific to flow control protocols, but let's try and show a type of diagram that we can use to illustrate how a protocol works. Up until now, we've mainly seen we send bits or signals across a link in one direction. But shortly we're about to see, well, now we send in one direction and we get a response in the other direction. What we're going to do in the next 3 or 4 slides is introduce one technique for illustrating such protocol mechanisms. And it's quite simple. Everyone knows the 5-layer stack. Here's an example of what happens. Computer A wants to send data to computer B. Then the user, say at computer A, presses send. It's a photo, some data. The data is processed by each of the protocols at the 5 layers and passed down inside the computer. And eventually the physical layer transmits that as signals across a link, and it's received and processed and passed up until computer B, or the person sitting at computer B, receives the data. The processing at each layer may have some delay, processing delay, and there may be some queuing delay at each layer. That is, the data comes from the transport layer, is put into some queue or memory at the network layer. It may have to wait before it's sent, some queuing delay. So we have processing and queuing delay at each layer, both transmitting and receiving. We know we have transmission delay across the link and propagation delay across the link. If we focus just on the on the data link layer, so just seeing from the perspective of the data link layer, the steps that occur are: first, data arrives from the higher layer, the network layer, step 1. That data may be queued, put in a queue, put in memory, and then it's processed. That may take some time. Then we transmit a frame. That frame propagates across the link. It's processed at the receiver, maybe some queuing delay, and then sent up to the network layer. That's just the steps that occur. This is a type of diagram that we can use to illustrate those steps, to try and understand how protocols operate. It's called a time sequence diagram or a message sequence diagram. It shows the the sequence of messages being exchanged over time. How we read it is computer A, computer B, and time is increasing as we move down. So these, we're going to show what happens, the events that occur at both computer A and computer B over time. So in this example, the first thing that happens from the data link layer's perspective is data arrives from the higher layer. So at this point, data arrives. Assuming that there's no processing delay, in this case, immediately computer A transmits a frame containing that data. And the way we illustrate that is using this rectangle here. This illustrates the time it takes to transmit the frame. Think of, we start a clock. We start our clock at the start, and the clock is increasing as we move down. So at this point in time, we start transmitting the frame. We're transmitting bit by bit, the frame across the link. We're transmitting, and here we've finished transmitting the frame. So this diagram is just a way to illustrate what happens at both the sender and receiver. The rectangle, the transmission of a frame. But we know when we transmit a bit out of our computer, then that bit is sent actually as a signal across a link, and that signal takes time to propagate to the other side from A to B. So there's some extra delay of propagation delay in this case. And that is shown by, if we transmit the first bit here, it takes some time before that first bit is received by B. So the time between here and here is the propagation delay of that first bit. And when we transmit the second bit, or the signal representing the second bit, that also has to propagate across the link. So, although it's not shown explicitly here, the second bit is transmitted, and that propagates and then is received sometime later. And the third bit and the fourth bit and the last bit is transmitted at this point in time, because we transmit the frame bit by bit. The first bit, the last bit, and the last bit propagates, and the last bit of the frame is received here. So in fact, from the receiver's perspective, the thing that's important is when is the entire frame received. Because normally we cannot do anything until we have the entire frame. So at this point in time, the last bit has been received, the entire frame has been received, and we can process that frame and send it, in this example, to the network layer. That is, we've delivered that frame from A to B. So this type of diagram we'll see in a number of cases when we try to describe how protocols work, because it shows the timing of how things work, or the timing of the operations, the time of transmission, the time of propagation. We could also show the time of processing and queuing delay. So the propagation and transmission times or delays are shown there. Of course, you can calculate them if you know numbers. If you knew the distance of the link, and if you knew the speed of the signal, you could calculate the propagation delay. And similar transmission time, you can calculate that. So these types of diagrams we're going to use to describe our protocols. So now let's look at our first flow control protocol. It's called the stop and wait flow control protocol. It's a general mechanism that can be used in different specific protocols, but it's quite simple. Remember, the aim of flow control, make sure the sender does not send too fast for the receiver. Control the speed at which the sender sends. And in stop and wait, it's very simple. What we do is transmit one data frame, and we do not transmit the next one until the receiver allows us to. So in the stop and wait flow control, we have two types of frames. One is the data frame, and that's a frame that contains the data that we want to communicate, plus some header normally. That is, we have the bits that we want to communicate, plus some header to assist with the protocol. And we have a different type of frame, an acknowledgement frame, an ACK frame. This is sent from the receiving entity back to the sender saying, I acknowledge the receipt of the data. That is, if I receive data, I can send an ACK back. So we have two-way exchange of frames in this case, a data frame and an ACK frame. A protocol is defined by the types of frames, the formats of those frames, and the set of rules that the entities follow. So we can summarize the set of rules for stop and wait as these 4 rules. The source that wants to send the data transmits a data frame. Then, after transmitting the data frame, it must wait for an ACK frame before sending the next data frame. So if the source has a lot of data to send, a gigabyte of data, and there's some limit on how much data is allowed to be put inside one frame, let's say 1,000 bytes per data frame, the source sends the first 1,000 bytes in a data frame. Before it can send the second 1,000 bytes, it must wait for an acknowledgement to come back. That's where the name stop and wait comes from. You transmit a frame, you stop and wait for an ACK before you transmit the next frame. From the destination's perspective, when we receive a data frame, we may reply with an ACK if we're ready for more data. So this is where the flow control comes in. The destination receives data, puts it inside memory. If we have enough space in our memory to receive more data, we can send back an acknowledgement. And that acknowledgement will allow the source to send more data. But if we receive a data frame and that means our memory is now full, then we do not send back an ACK. And therefore the source cannot send more data and not overflow the receiver. So in fact, the destination can stop the flow of data by not sending an ACK. And they're the basic rules of stop and wait flow control. Here's an example, just an example of the exchange of those frames using our timing diagram. In this example, we have data arriving from the network layer at computer A, and we want to send that data to the network layer at computer B. The data arrives from the network layer at different times. We can think of it as random. That is, data comes when maybe the user at computer A does something. You click on a link, that triggers data to be sent from the network layer. Sometime later, you click on another link and more data arrives to be sent. So in this example, we've got data arriving at 3 different times. Remember, time increases as we go down. So this illustrates how the stop and wait works. At the start, data arrives from the network layer. Let's call it data 1. The data link layer protocol, the stop and wait flow control protocol, puts the data inside a frame and distinguish between the real data, data 1, and a data frame. A data frame may contain the real data plus a header. So the size may not be identical between the data, the real data, and the frame. And we transmit that frame. So we transmit the first bit, the second bit, and up to the last bit. That takes time, and it takes time to propagate across the link. This diagram shows just when is the last bit received. Just to make the diagram clearer, we don't show the propagation of all bits. We don't have an arrow for bit 1, bit 2, bit 3. We just show that when is the last bit received. Last bit was transmitted here, last bit is received at this point in time. The difference in time between here and here is the propagation delay. So in this example, B receives the data frame, and let's say the buffer at B was full when after it received that data frame. So if we had a buffer size of, say, the buffer at the receiver, or the memory at the receiver, had a maximum size of 1,000 bytes. So, and let's say each data frame contains 1,000 bytes of data. Then initially the buffer is empty at B. When we receive the first frame, we put the data received into the buffer, so now the buffer is full. So we have no more space in the buffer, and therefore we cannot allow the source to send another frame, because if they did, we would overflow our buffer. So we wait for space in the buffer to become available. Why does it become available? If the data in the buffer is delivered to the network layer at the receiver, then we can remove it from the buffer. Space becomes available. So the delivery of the data to the higher layer, and that's what this arrow shows, means we now have more space in the buffer, which means we can send an acknowledgement back. So an ACK is a special type of frame. In this case, it contains no data, it's just header. It's transmitted back, propagates. When it's received, the source, computer A, can transmit the next frame. So note what computer A did. It transmitted the frame and then it stops and waits for an ACK before it does anything else. So it's waiting for an ACK, it's waiting for an ACK. In the meantime, more data came from the network layer at computer A. We've got more data to send. We cannot send that yet because we haven't received the ACK for the first frame. So we're waiting, we have data ready to send. We're waiting, we receive the ACK, now we send this data in the second frame. Transmit the second frame. In this example, it's received and immediately the data is delivered to the network layer at the destination B. Send back an ACK. The ACK is received by computer A, but we have no more data to send in this case. So we do nothing. Then we have data to send. Since we received the ACK previously, we can immediately transmit this data frame. This diagram is incomplete. We'd have a propagation, ACK, and come back again. So it could keep going. Data could arrive, and we keep sending data, ACK, and so on. So there is, in the previous class, some questions were what happens after this? Well, you should be able to work out. There's going to be propagation. Eventually, an ACK should come back, which will allow us to send more data. In this example, in this case, we had to wait for buffer space to become available. Here, immediately the data was delivered to the network layer, which meant we could immediately send back an ACK. We cannot predict what will happen in real life. It depends upon the computers doing the processing and the applications and the protocols. Similar, we cannot, in some cases, predict when is the data going to arrive from the higher layer. It may depend on many factors. The speed of the computer at the source, what the user is doing, what protocols are being used. So sometimes we think of data arrives either randomly or all arrives at once. How big is the ACK frame here? It's small. That is, usually we think of it as just a header, contains no data. We'd like to keep it as small as possible. We'll see some examples. Bytes, tens of bytes would be ideal. Different real protocols would specify the size of the ACK frame. This is just the general mechanism. So, solve this problem. From the operation of the stop and wait, we can calculate the timing of all the events. How long does it take to transmit, to propagate, the process, and so on? So here's a scenario. The source has 3,000 bytes of data, of real data to send, and it has that at the start. We can only transmit, each data frame contains a maximum of 1,000 bytes of real data, and it also contains a header of 20 bytes. An ACK is 20 bytes in this example. The destination, when they receive a data frame, they process for 1 microsecond, and then they can send back the ACK. And we have the characteristics of the link, 2 kilometres, 1 megabit per second data rate, and link speed or a signal speed of 2 by 10 to the 8 metres per second. You need to calculate what is the throughput with these 3 frames, or maybe more a better question, what would be the throughput if we had an infinite number of frames? This question asks or says we have 3 frames. What if we had 3,000 frames or 3 million frames? What's the throughput? So you should start trying to answer that in the next 5 minutes by drawing the diagram of what happens. It doesn't have to be to scale, but if you draw the diagram, then you can start to work out the timing of the different events. So you need some paper, preferably a pen or a pencil, or a computer is fine. You don't need to wait for me. So with that scenario, you want to draw a diagram similar to this that shows the exchange of the frames. And then you'll need to calculate the timing of each of those activities. For those waiting for me, then here's your help. That's to get started.
Assuming that the buffer size is unlimited, or is it only?
So in this question, there's nothing about what's the size of the buffer at the receiver. So in reality, we'd need to know that to see when do we send back a response. So I think in this case, assume that the buffer is unlimited, but take into account that there's a 1 microsecond processing delay. That is, when we receive the data frame, we process it for 1 microsecond, and then there's space in the buffer for more, so that we can send back an ACK. We will see a case where the buffer is limited after this one. This is the easiest case. The diagram is relatively easy to draw. It's the calculations that make it a little bit harder. So I see people with a diagram which is not the same as, but is similar to this one. But now you need to find the throughput. The hint is find the total time it takes to do all of that, to transmit that data. Find the transmission time, propagation time, and so on. This arrow that I used to show something coming into A and similar going out of B indicates data arriving from the higher layer. Remember this? What we're showing is the interactions between the data link layer protocol at A and B. But what triggers the protocol to start is that we receive data from the higher layer, which is the network layer. That's what this arrow shows here. At this point in time, we receive 3,000 bytes of data from the network layer. We now need to use the stop and wait flow control to deliver that to B. This is 3 by 1,000 byte messages. I've combined them together here. Anyone have an answer of how long it takes to transmit the first data frame?
Is the throughput about 980 kilobytes per second?
About 980. That's close. Depends exactly how we calculate it. You're about to say it's not correct, but it's close. There need to make some assumptions to get the exact value. So we have data to send. We create a data frame. That sounds close. This rectangle indicates the transmission of data frame 1. If I drew data frame 1, then I could draw it like this. It contains some data plus a header. And we know the size of the data is 1,000 bytes. That's from this part of the question. Each data frame contains 1,000 bytes of data plus 20 bytes of header. So the total size of the data frame is 1,020 bytes. Data plus header. And the time it takes to transmit, therefore, is using something we learned in the first or second lecture. Transmission time is the data size divided by data rate. The transmission delay of the data frame size, 1,020 bytes, divided by data rate, 1 megabit per second. We can send 1 million bits per second, we've got 1020 bytes. How many seconds does it take? 8.16 or 8,160 microseconds. 1020 times by 8 is 8,160 divided by 1 million, 8160 microseconds. That's the time to transmit the data. We illustrate this on the diagram. One way to think of it is that when we start, we use a clock that starts at time 0. This time here, t time equals 0 microseconds or 0 seconds. And we start transmitting the data frame. We transmit the first bit. How long does it take to transmit one bit? To transmit one bit? We're transmitting 1 million bits per second, therefore one bit would be 1 microsecond. Transmit the first bit, it takes 1 microsecond. The second bit, the third bit, we've got 8,160 bits to transmit. It takes us 8,160 microseconds to transmit the entire frame. Therefore, the time at which we've transmitted the last bit would be 8160. I'll leave off the units here, assume all the blue ones are in microseconds. Start at time 0, finish at 8160. I've just included this because it's useful to see the timing of each of the events to see how long everything takes. Of course, when we transmit a bit, think of that bit is converted into a signal, and then that signal propagates across the link. So the first bit we transmitted at time 0, and then that signal propagates. And it takes time to get across the link. From A to B, it takes the propagation delay. And the propagation delay, in our case, 2 kilometre link, 2 by 10 to the 8 metres per second is 10 microseconds. 2,000 divided by 2 by 10 to the 8 is 10 microseconds. So the first bit that we transmitted at time 0 arrives at B at time 10. Imagine both A and B have synchronized clocks. If they both start at the same time and the clocks are counting, then transmitter bit is going to arrive 10 microseconds later at B. 1 microsecond later we transmit the second bit, and that propagates and arrives. I will not draw it here. And then the third bit and the fourth bit and then the 8,160th bit. And instead of drawing it as a, say, some shape of an analog signal, we'll just keep it simple and draw it as an arrow to represent the propagation of that last bit. So the first bit is received, and then you don't have to draw this part. I'll explain what it means. During this time, B is receiving bits of the frame. The first bit through to the last bit. And we've received the entire frame at this time. Which is what? Yeah. If we transmit at 8160 plus 10 microseconds to propagate, 8170. So we've delivered the first data frame from A to B. By time 8170, B has received the entire frame. It can process that frame and then respond or act on that. And in our case, we assume that it has buffer space available. It takes 1 microsecond to process. Let's draw So this is not to scale, but we have some processing time in here. 1 microsecond later, which would be equal to 8171, we've processed that frame. And what do we do next? Send an ACK. When we receive the data frame, if we have space available in the buffer, we can send back the ACK. And we're assuming for simplicity that there's always space in the buffer in this case. So after processing, we transmit an acknowledgement in response. We'll draw that. And we need to transmit the ACK bit by bit, same as the data frame. The size of the ACK is 20 bytes, 160 bits. Therefore, it's going to take 160 microseconds to transmit the ACK. 160 bits divided by 1 megabit per second gives us a transmission time for 160 microseconds. Make note of that. Transmission time of the ACK is 20 bytes divided by 1 megabit per second, 160 microseconds. So we start transmitting the ACK. We finish transmitting the ACK at time 8171 plus 160. And similar, the ACK propagates back to computer A. The first bit propagates, I will not draw that. The second bit, the third bit, and the last bit propagates. We'll just draw that. And in this case, the link is the same distance in both directions, and therefore we have the same propagation delay in both directions. Another 10 microseconds to get back. So from A's perspective, coming back to the start, we start transmitting our first data frame containing 1,000 bytes of real data. Transmitting, 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 finish transmitting. Now we stop and wait. We're waiting for an ACK to come back. Waiting, waiting. We cannot send any more data. We have more data to send. We have a total of 3,000 bytes to send. This contained just 1,000 bytes. We have another 2,000 to send. We're not allowed to send any more. We're waiting for an ACK. We're waiting. At this point in time, when the first bit propagates back, it should be 8181. That is 8171 plus the 10 to propagate, 8181. We start receiving the ACK. We're receiving the ACK, receiving, and we've received the entire ACK by time 8341. We transmitted the last bit of the ACK at 8331, propagation of 10, received the last bit of the ACK at 8341. Now we've received the ACK, and now we can send more data. Any questions so far? We'll continue. It gets easier because everything just repeats. Yep.
What about the propagation delay of the app?
So this is the propagation delay of the ACK. That is everything that we transmit. The ACK is 160 bits. We transmit the first bit. It propagates. The first bit arrives. When the first bit is propagating, we're actually transmitting the second bit as well. And that propagates. And the third bit, we just don't show it graphically here. Just in most cases, it's sufficient to show just the last bit being propagated or the time it takes. transmit at 8171, we'd receive that at 8181. Propagation delay is the same in both directions, 10 microseconds, same distance. So both frames have some propagation delay. We care about when we've received the entire frame, and therefore often just show when is the last bit received. Any more questions on this part? Any questions over here? What happens next then? The next data frame is transmitted. Good. Stop and wait. We have 3,000 bytes to send. We just sent 1,000. We stopped and waited for the ACK to be received. We're now allowed to send more. Since we have more to send, we'll immediately send more. Transmit data frame 2. How long does it take to transmit data frame 2? Another 8160 microseconds. Everything's the same for the next data frame because same size, same data rate. So if we start transmitting at 8341 plus 8160 is what? Is that correct? We're going to run out of space. So if we continue our diagram across here, we finish transmitting the second data frame at 16501 here. Propagation, another 10, brings us to 16511. Processing, 1, brings us to 16512. Transmit the ACK back in response, another 160. 16672, and propagation another 10. So at time 16682 microseconds after the start, we've now delivered 2 frames and they've been ACKed by the receiver. Time 0, the first frame containing 1,000 bytes of real data. We receive an ACK, transmit the second frame, propagates, process, send back an ACK. And then because we had 3,000 bytes of real data, we need to do it again. What's the time here?
It is necessary to wait for ACK.
Let's wait for the ACK and see why we want to care. Why we care about that.
Make sure that the data has sent correctly.
Yeah, although we assume that there's no errors in this case, in reality we'll usually also use the ACK to make sure that there are no errors. If we receive the ACK, it means they receive the data. So note that the first, let's call this the first phase. Send the first data frame, receive the ACK. The time that took was 8341. The second phase, when we send the second data frame, it starts at 8341, finished at 16682. What's the difference? 16682 minus 8341 is, let's draw it. If I zoom out, this is what we have. 3 data frames. The transmission and the acknowledgement of each frame takes the same time. That is, the first one took a total of 8341 microseconds from 0 to 8341. The second one, up to 16682, takes another 8341 microseconds. And the third one, the same amount of time. Because nothing's changing. Same data size, same delays. And in fact, if we extended this to have 1,000 messages instead of 3 messages, it'd be the same. It'd just keep going. Transmit, receive the ACK. Transmit, receive the ACK.
Why does a third frame still need to wait for the ACK signal? Because it's already sent.
It depends on what the source is doing. That is, let's say we only have 3 bytes, 3 messages to send at this point in time. Sometime later we may have more. So we need to wait for the ACK if we want to have more later. So we're just looking at some portion of time where we just have 3 messages. But in general, we may be sending messages back and forth, and we may be sending over a longer period of time. And therefore, we'd need to wait for the ACK if we wanted to send another piece of data sometime later.
So should we assume that there's the same number of ACK signals as the number of frames?
In this stop and wait, yes. We send one data frame, we receive an ACK. Data, ACK, data, ACK. So no matter how many messages we want to, or frames we send, it should always be followed with an ACK, if everything goes correct. And let's say, and it's more practical, if we have more than 3 messages, we have a large number of messages, we look at what's the average rate at which we're sending data. Well, in this phase, we sent 1 data frame. The amount of real data we sent was 1,000 bytes. Our data frame contained 1,000 bytes of real data plus 20 bytes of header. So in that period of 8,341 microseconds, we transmitted 1,000 bytes of real data, and that 1,000 bytes was successfully received. And then in this next period, we transmit another 1,000 bytes, and that's successfully received. And in the next period, another 1,000 bytes is transmitted and received. And if we kept going, the pattern is we're transmitting 1,000 bytes every 8,341 microseconds. And from the receiver's perspective, we're receiving 1,000 bytes of real data every 8,341 microseconds. That is, the receiver receives 1,000 bytes, then receives nothing, and then receives the next 1,000, the next 1,000, and if we kept going, every 8,341 microseconds we receive 1,000 bytes of real data. And that gives us our throughput, because throughput is the rate at which we receive real data. We're receiving 1,000 bytes, throughput, 1,000 bytes every 8,341 microseconds. And with a calculator, I think it's around 959 kilobits per second. So if we look at the average throughput, if we looked over a long period of time when we had a lot of data to send, we'd average about 959 kilobits per second, or 0.959 megabits per second. Our link data rate was 1 megabit per second, 1,000 kilobits per second. We're getting a throughput of 959 kilobits per second. We have a link efficiency of 95.9%. (959 kilobits per second is the rate at which we're receiving real data, but our link data rate is 1 megabit per second. So we can say the link efficiency is 95.9%. We're using 95.9% of the link to transmit real data. The other 4.1% of the time we're either sending header or we're not sending anything at all. Because in some cases we send nothing across the link, and that reduces the efficiency.
Everything you got before should be 98. No delay like this.
Yes, so up until the midterm we had a very simple view of throughput. We just looked at the data, the real data divided by the total packet size, like 1,000 divided by 1,020. But that's only the case if there's no time spent not sending. In most most protocols at the data link layer and above, we're transmitting, but then there's a period of time that we're not sending anything. From an efficiency or a throughput perspective, that's a waste. We'd like to spend all of our time sending real data. In fact, in this case, we're spending some time transmitting header, that's an overhead, and we're spending some time not transmitting at all, in fact down to here. So in this period of time, we're sending real data in this portion, and where we have red, we're not sending real data. And that's our measure of efficiency. We'd like to minimize these red parts and therefore increase the efficiency at which we use the link and increase the throughput. So now the way that we calculate throughput is not as simple as before we did before the midterm. We need to consider that sometimes we don't send anything, and that reduces the throughput. And the way we calculate that time is using this approach of working out how long does it take to get the data frame and get the ACK back.
Only when we cut frame, if we send the data from my computer to the back drive, use physical data now it's not like the frame. It's not cut the data to be frame or send all.
It depends on the protocol being used. If you're using a protocol like a stop and wait protocol or similar, where you have to stop and wait before you receive, before you can send more, then yes, you need to consider this. And it may be, I don't know in the case of USB, what data link layer it uses. How do we increase our efficiency? Increase the efficiency by increasing the frame size relative to everything else. Instead of 1,000 bytes, send 10,000 bytes. per frame. If we have enough data, we can fill up that frame. Why would that increase the efficiency? Because we'd spend more time transmitting real data as a fraction of the total time than if we have a smaller data frame. The header relative to the total frame will be smaller. What else can we do, or what other factors impact upon the efficiency? Size of frame. Someone said that already. What else?
Increase size of act.
Size of the ACK. Okay. So the ACK, in our case, took 160 microseconds. That is a time where we're not sending real data. If we make the ACK smaller to 10 bytes, it would just be 80 microseconds. And instead of 8341, it would have been, minus 80, which is 8261. And that would have increased our throughput if we divided by 8261. Reduce the size of the header relative to the data. Reduce the size of the ACK relative to the data. What else impacts on performance? We may not be able to control it, but what? Distance. More generally, propagation delay. In our case, the propagation delay was 10 microseconds. What if it was 100 microseconds? A quick calculation. Everything's the same except the propagation delay is increased by a factor of 10. We'd get the same shape of diagram. 8160, 100, 1 of processing, 160 of the ACK, another 100. Total would be if we increase the propagation delay, the total time to deliver that same amount of data increases. Propagation increased from 10 to 100. The total time increases. Throughput is the data delivered divided by this total time. If this goes up, throughput goes down. So in fact, the key factors are the relationship between the propagation delay and the transmission delay. This tries to summarize the efficiency which relates. We see the general equation. The best case, the amount of data. In our case, we had 1,000 bytes of data divided by, or the efficiency is the time to transmit that data, divided by the time to transmit the data plus the header, because we have data plus header plus the ACK plus 2 times the propagation delay, because we have to propagate the data there and propagate the ACK back. If we ignore processing and queuing delay, that's a general form of the efficiency. To make the efficiency go up, you either increase the time transmitting data, increase the size of the data, or decrease the header, decrease the ACK, decrease the propagation delay. So those are the factors that impact upon efficiency.
How we spell this side?
N, eta. It's generally used for efficiency or as a measure of, it's Greek, isn't it? Eta. Not N efficiency. N is the Greek character for E, or close to E. Or no, eta. E is epsilon.
And the unit of norm is no unit because
efficiency, the no units. So it's a ratio between two values of the same units. In this case, these are all representing time. Time divided by time gives us no units. Tomorrow we will look at another case that illustrates the efficiency, another example, and then we'll move on. How can we use a different protocol to improve the efficiency? Stop and wait's one flow control protocol. Tomorrow we'll look at an alternative sliding window.